Hello everyone, this is group number 16. Our seminar topic is innovative heatsink in electronic packaging. We have the group member of four papers. First is Ruturaj Marathe, second Debashish Suryabansi, third is Amar Ray, and fourth is Manjeet Kumar. This is how we are proceeding with the content one. This is all as follows. We have seen in this content. The next slide is a problem statement. In this problem statement, we have to know about how the heat sink work. The heat sinks have been long been used to manage heat in electronic devices, transferring excessive heat from the crucial components. The traditional designs such as finned heat sinks and fan exchange heat sinks rely on the conduction and convection. These heat sinks are widely used due to their simplicity and reliability. However, as electronic devices become more compact and power dense, traditional heat sinks face challenges such as inefficient heat efficiency, large space requirements, and limitation in cooling high performance components. These limitations have driven the need for innovative heat sinks designs, which we have explored next.
So moving on to traditional heat sinks used in electronic packaging. Generally, traditional heat sinks are divided into two types: passive heat sinks and active heat sinks. Passive heat sink uses natural convection, whereas active heat sink uses forced convection. Passive heat sink then subdivided into pin type and plate type, generally used. Then it can be subdivided into many categories depending upon the manufacturing process, like casting, forged, extruded, skype type. You can see these are the following are the examples of different types of heat sinks. Similarly, active heat sink is then divided into some power process cooling, like you can use fan, water pumps, etc. And second one is heat pipes, heat pumps, and other phase change metals, and thermoelectric metals. Such kind of comes under active heat sink. Following are some existing issues with traditional heat sinks, like limited heat transfer efficiency, space constraint, cost and complexity, fouling and maintenance, pressure up and energy consumption, and thermal resistance. Coming to limited heat transfer efficiency, traditional sinks often rely on simple fin designs, which can be inefficient for high power electronics. So the heat transfer rate is limited by the surface area and the thermal conductivity of the material. So next, coming on to space constraint, an electronic device where like narrowing all the parts and increasing IO density. So heat sinks need to be that much constraint to uh, transfer effectively. Then cost and complexity. If we're narrowing the sizes, so the complexity and the cost equally increases with the size. Then for fouling and maintenance, like after multiple uses, some particulates and corrosions are being deposited over heat sinks. So regular maintenance are needed. That is one costly part. Then coming on to pressure drop and energy consumption, over the time, in generally in case of active heat sinks, the flow of air, water, and other things, eventually the pressure drops and energy consumption increases. And with the corrosion and other surface defects, uh, thermal resistance increases. So you can see these graphs, like for metal and metal P, how the heat transfer efficiency is dependent, and space constraint and cost and complexity, like traditional and between traditional and advanced. Similarly, fouling and maintenance, it kind of linearly increasing with time, pressure drop and energy consumption, and thermal resistances. Before moving on to advanced heat sinks, you can optimize the traditional heat sinks by optimizing some of the parameters, like optimization of heat sink shapes, like simply using parallel and counter heat sink channels. We can use some bifurcated designs, like such kind of snowflake design, honeycomb designs, and arrow-like designs. These kind of designs we can use to optimize the heat transfer. Similarly, in second point, you can use secondary flow initiator like vortex generator, like active parts, adding some active parts or small winglets to the fans or heat pumps, etc. These are some different kinds of winglets, and accordingly you can see the how velocity of the velocity of air varies in fin tip heat transfer. With first one is without but vortex generator, and others are modified vortex generators. Similarly, some surface depression and protrusion can increase heat transfer, and fouling, uh, to avoid fouling and other depositions, we can add a fouling protection layer over the heat sinks to increase its heat efficiency. You can see a graphical representation of temperature or heat map, a simple FinTep, how the temperature varies from TIM to FinTep.
Okay, so coming towards advanced heat sinks, there are three types that we are going to discuss. The first one is modular heat sink, the second one is multifunctional heat sink, and the third one is 3D printed heat sink. So in particular, modular heat sink, what happens is there are two layouts that is shown in figure number 5, that is full heat sink layout FHS, and in diagram C, modular heat sink layout, that is MHS. So in FHS, what happens is we take all the components in particular layout, but in modular heatsink, we take individual components in that particular layout, and we have different kinds of heat sinks that are shown in figure number 6. Like there are short and long, tall kind of fins that we use here. So what the study shows is that in key findings, we can see that the tall modular heatsink shows the best cooling performance in all of this particular type. In figure number 6, this is a top view and side view of a particular type of heatsink. Then comes another finding is that reduce maximum system temperature by 8% compared to the other configurations. So this particular thing we see in modular heatsink. So coming towards the second type of advanced heatsink, that is a multifunctional heatsink. So in multifunctional heatsink, we use different techniques like 3D printing, electroplating to create complex geometries. So why complex geometries? Complex geometries are useful to facilitate different kind of heat mode, that is conduction, convection, radiation. So that is one of the features, that is enhanced heat dissipation. So that we can see in this particular thing that Dr. Shankar Krishnan and Dr. Sripriya Ramamurthy from our institute only, they have studied this particular thing and got that this electroplating and 3D printing has improved the efficiency by 50% than the conventional heats. So second comes the integrated functions. So here we can integrate different function at the same time, like mechanical stability, noise reduction, and the heat dissipation. So another feature is advanced materials and techniques are used in this particular. So what are the applications? So in high density electronic assemblies, high power electronics where input output and pitch size is very low, we require very high speed, good signal integrity. So there we can use this kind of heat sinks, and also the noise reduction. Then comes the third advanced heatsink, that is 3D printed heatsink. So what are its advantages? As we can see in these particular figures, that we can get 3D printed heatsinks of different kinds, different shape, different sizes, made of different materials. So as all of these figures are complex geometries and they are customizable, so that is one of the advantage. Then material optimization, we can use multiple materials that are that we can 3D print actually in this particular thing. Then wet reduction and compactness, low density materials with having high strength, high mechanical strength can be used here, so which can improve reliability and efficiency of this. But what are the disadvantages are material limitation, not all materials we can use for 3D printing. Then comes surface roughness and post processing. As we know that 3D printing sometimes required post processing so that to improve its surface finish. Then comes the design and manufacturing constraint and very high initial cost for this.
Now coming to the future research trend in heatsink technology, uh, as electronic device become more power dense, research in focusing on new materials and cooling methods. So for this I have a two like advancement, that is one is academic advancement. In this academic advancement, there is graphene and carbon nanotubes, that is ultra high thermal conductivity materials for efficient heat dissipations. And the second one is micro channel heat sinks, that is teeny fluid channel increase surface area for better cooling, ideal for high powered electronics. And coming to the industry innovations, the first one is 3D printed heat sinks. That is, companies are adopting additives manufacturing for lightweight, high performance heat sinks. The second one is high performance thermal interference materials. That also we can call this TIMS. That is phase changes materials that adapts to temperature changes for better cooling. So now coming to the micro channel heat sinks, that is MCHS. In MCHS, an advanced cooling solution for electronics, different channel shapes, that is rectangular, trapezoidal, circular, and arrangementals like single and double layers optimize heat dissipations. These structures enables customized cooling for high power electronics, making MCHS essential for modern thermal management. So there are advantages and disadvantages. So coming to the advantages, high high heat transfer efficiency, compact design, uniform temperature distribution, scalability, energy efficiency, customizability. And now coming to the disadvantage, high manufacturing complexity, susceptibility to fouling and closing, pressure drop issues, thermal stresses, limited fluid choices, and maintenance challenges. These are the disadvantages. Now coming to the conclusion part, in conclusion, managing heat in electronic device is very important to keep them running efficiently and prevent damage. Traditional heat sinks helps, but they are not always enough for modern high power electronics. The second one is our research shows that modular heat sinks perform better by improving heat transfer and lowering system temperature. New technologies like 3D printing, advanced materials such as graphene, and microchannel designs are making heat sinks more efficient and compact. And the third one is, as electronics device continue to get smaller and more powerful, better cooling solution will be needed. Ongoing research and innovation in heat sinks design will help improve the performance and reliability of future electronics. Here are the references. Thank you.